I'm Bill Gropp, Director of the National Center for Supercomputing Applications at the University of Illinois and Vice Chair of SC20 Invited Talks. Welcome to the SC20 Invited Talks session on post-von Neumann architectures. The overarching theme of SC20 is more than HPC. Complementing this theme, the Invited Talks collectively focus on applications and technologies impacting all areas of science, engineering, medicine, and society. The distinguished speakers in this session give us a view into the future where post-von Neumann architectures are expected to play a transformational role alongside and complementing mainstream technologies in supporting ever-complex scientific workflows. Ronald Luijten is the initiator and was senior technical project leader of the DOME hot water-cooled micro data center project. In 2019, Ronald was on sabbatical at ETH Zurich, architecting a non-von Neumann weather climate code accelerator called Cloudchaser, and his personal research interests are in data center architecture and design and performance. Early this year, Ronald retired from the Zurich IBM Research Laboratory in Switzerland. He is pursuing building the Cloudchaser accelerator through his new company.
Hi, my name is Ronald, and I'm pleased to talk to you today about a project that I started at the ETH in 2019 called Cloudchaser, which is a new accelerator for weather and climate codes. So I know that these are somewhat unusual circumstances that you're watching this, and thanks, by the way, for joining, and also thanks for the organizers to have me here today. Some of you are probably watching this as a recording, and if you want to save some time, I'll be spending about 6 minutes on the key results first in this presentation, then I'll dig into some details, and that'll take about 25 minutes, and then I will follow by performance and conclusion. So if you want to save some time, you can skip the middle, but you're more than welcome to stay for the entire thing, obviously. So people that know me have seen me say this before: compute is free, data is not. And in this project, I am actually living this. So I took this advice that I gave everybody also to my own heart, and this is what I'm doing. So key results first. So it immediately goes into a lot of detail. Basically, Cloudchaser is a weather and climate accelerator that we would have to build into an ASIC based on an architecture called CGRA, or Coarse Grain Reconfigurable Architecture. And that is basically an array of units that you see here that are located on a chip. The twist that I have in my architecture is that the memory is distributed evenly over the chip. So some of the units are memories with the hashtag, you see that here as a cache, and others are processing elements where the compute is being done. And the real innovation that I have is that the memories located on the chip actually physically correspond to the grid tool points for the software on the planet, right? So the grid mapped on the planet, those grid points physically relate to the physical locations on the CGRA. I've not seen anybody else do this, and the reason why this makes sense is that the Stencil compute kernels are used to solve this partial differential equations, because with this type of solver, you actually have only nearest neighbor communication. The fact that we have nearest neighbor communication actually results in very low wiring requirements on the chip. So there are no global wires that need to go from one end of the chip to the other end of the chip to do the actual computation. That I apply this at the level of chip, I have not seen anybody else do before. So the Cloudchaser CGRA architecture in a system would look like this. So we have an accelerator chip that is connected to a host with a coherency bus that has its own DRAM and network adapter, and the accelerator has its own DRAM, which in my preferred version would be 4 times in HBM2, giving you 1 terabyte per second bandwidth over the bus. This DRAM would be mapped into the kernel space on the host through the coherency interface. And the way that we run a stencil is that we pre-fetch the data from the DRAM with full speed to the on-chip cache. There's no contention there. And once the data has been prefetched, we then have configured the computation and the wiring for the CGRA to actually run the stencil. With this comes, of course, a whole tool flow. So this project, we have co-designed the hardware and software together to make this all work. The people at CSCS have developed a domain-specific language, DSL, that has the high-level description of the entire die core, which through a graph mapping to the CGRA results in the bits that are needed on the accelerator chip that then drives the sequencer and the runtime support that is on the host. So the result of all of this is that we have a new solution that can be used for any problems that are using stencil compute kernels for regular 2D and 3D grids. So for irregular grids, it will not work. But it still addresses about 30% of the HPC applications. This solution is about 3x faster wall clock time than the best GPU that you can get today. And I think it's about 10x better energy to answer if I compare this with a 4 HBM baseline solution. Interestingly enough, the performance scales linearly with the memory bandwidth attached to the accelerator. So if you want to calculate the system performance, you figure out how much data you need to move from the DRAMs to the caches. You figure out the bandwidth, how long it takes. You figure out how many of those memories you have in the system, and you know the system performance. But what I haven't mentioned is that the memory has been designed with 3 pragmas, which is that to do a stencil calculation on a 3D grid, I call that a sweep, all data points that are necessary to do the calculation may be read from HBM only once. Number 2, all data that is read over the memory bus into the accelerator must be used in the computation. And number 3, the bus will run at maximum speed all of the time. The only thing that I allow is the refresh. So you get the maximum out of your memory subsystem. The code generation for all of this is directly done out of a domain-specific language. I wrote a simple compiler in Python, single-threaded, that compiles this for a stencil in a couple of minutes. And the feasibility of this solution is, in fact, given the exploitation of the locality properties of the stencil computation, as I mentioned. So we know that we can build this into an ASIC. So Professor Schultes, who enabled my sabbatical at the ETH at some point in time, actually said, this is a foundational concept, just waiting for someone to write it down. So I guess that I'm the lucky one who writes this down. So much for the key results, and let's dig into the details. So why did I get into this project? So one of the things that I learned in my 35 years in research is it is a really good idea to do something rather different every 7 years or so. In my previous project, you probably remember that I did the micro data center, so the hot water cooled micro data center, for which I got an award from Hyperion. One of the key learnings in that project was that it's a good idea to motivate yourself to get out of bed each day, even when things in the project are getting somewhat hard, by leveraging personal interest. Now, you see that I have another interest in clouds from a personal viewpoint, which is, by the way, why this thing is called the Cloudchaser. And the weather is really important for me, and I noticed that the weather prediction in the Alpine region in Switzerland is not always that accurate. So I just thought those weather forecast people can probably use some help. My last international assignment was 1995, so I decided that it's a good time to get some fresh air. And I'm very grateful for Mauro Bianco from CSCS at an SOS meeting a few years back to describe the stencil problem, because when I saw that, I said, oh, this looks really interesting. I want to dig into that at some point in time. So CSCS has ported the COSMO application to their GPU cluster, and it's the first one that actually was using GPUs in weather production. And COSMO uses a Cartesian structured grid. You see a picture here. And with the stencil-based solvers, you can easily distribute this over a cluster. And so here you see an example of 2 nodes in this cluster, and it will, scale in the XY direction to more. But here you have the kind of the blue node and the green node. And the key advantage of this solution is that for the blue node to do the calculation, it needs access in the halo region of its neighbor's data only for the size of the halo. In this case, it's 3. And this means that the center data points here are never directly communicated to anybody else. And the same applies to the green node. And this is the nearest neighbor communication need that this solution requires. Typically, what you have in a compute node is a grid of 128 by 128 by 88 to get super high performance per node. And then, of course, you need many nodes if you have like a 5,000 by 5,000 grid to do the entire calculation. Now, the weather forecast code is old and complex. And this diagram basically illustrates the complexity of the COSMO dynamical core, which is a directed acyclic graph you see here. And there are composed stencils, which are the purple boxes, halo updates, which are the green boxes, and boundary set conditions, which is basically a simple stencil, which are the orange boxes. So every 10 seconds time step, you walk through this entire data flow graph that goes kind of from here and it ends here. And you see that there are a boatload of stencils in there. So this is not a simple single stencil that you have to solve. And they have also benchmark stencils called horizontal diffusion and vertical advection stencils. And if you look at how the time is spent by the host on doing all those stencil calculations, you also see that the time used in computation varies from stencil to stencil, and there is no low-hanging fruit. So there's no single point where you can say, if I just solve this particular problem, then I'm home free and my work is done. So you have to do something that covers the entire die core. When you look at, so this is a zoom in to the same DAG that you saw before, and it basically shows that for each stencil you have a couple of arrays or 3D fields that are needed. The stencil has a name, there are dependencies, so you can only execute this stencil when this guy has been done, etc. many forecast programs such as COSMO or ICON and IFS are using those stencil compute kernels to solve those partial differential equations in the dynamical core. There are in the order of 100 different stencils used in a die core, and they're typically composed stencils. And the data is basically 100 or so 3D grids, also called fields, of which 30 are variable and 70 are temporary fields that are used. The problem when you try to implement this on a CPU or GPU is that the data access patterns are very bad for the typical caching mechanisms used on CPUs and GPUs. So people are already very happy when they get like 8% of sustained performance out of peak on a GPU. To zoom in a little bit more on what a stencil is, basically a stencil is a computation on a grid. In this case, we're trying to calculate a new value for the dark green point here in this 2D representation. And to calculate that value, you need to read all of those neighbors. And this is the neighbor access. The interesting point is that this addressing is relative, right? So there's no absolute addressing, it's relative to the point that you're calculating, which is here in the center. Now, this stencil is in fact the horizontal diffusion stencil, which is composed out of a Laplace, a flux, and a sum of fluxes that then generate the new value. The stencils used in weather applications are typically accessing neighbors in the I and J dimension only for the horizontal version, and in the K dimension, which kind of comes out of the screen here, for the vertical stencils. And those are typically alternating. Now, the data layout, so how you store your 3D fields in memory, you know, IJ first or IKJ methods, it is chosen in COSMO at runtime. And once you choose it, it's the same for all the stencils that are running, which means that, yeah, for some stencils, the layout will be better. For other stencils, the layout will be bad. There's no way to change the layout efficiently during the calculation, because then you spend so much time permutating the memory that also doesn't make sense. Mind you, there are, of course, boatloads of very experienced people that have worked on this for decades to get performance out of this. So it's not something that you can easily tackle by looking at a single thing. And the result is that when you look at academic work, there are plenty of examples in literature where people optimize an FPGA with a stencil, but for a single stencil only. They get superb performance for that single stencil, but it doesn't really help for the entire die core problem. Let's switch to CGRAs. So they are coarse grain reconfigurable arrays. They were first described in the literature more than 30 years ago, so the concept is very old already. What is new is that there is only good literature recently on how to map an internal representation or a data flow graph through a compiler onto the CGRA. 99% of the CGRAs are compute-centric. And the difference between the Cloudchaser CGRA and all the others is that this one is really data-centric. There was a very good paper published 4 years ago that took 25 years of CGRAs and put that into a nice picture that I show here, where basically it shows the relation of an ASIC and a CGRA and an FPGA and a CPU in a three-dimensional space. And when you look at what we're doing with Cloudchaser, we're implementing a kernel, a compute kernel, using a multi-op functional unit. Sometimes the CGRA calls it a functional unit, sometimes it's called a processing element, so those are the same. And those are configurable. Here is a example of a recent patent that actually was part of my inspiration. One of the contributors is my friend Al Gara from Intel, and this is the picture from that patent application. And what you notice is that this is a compute-centric CGRA design. Why do I say that? Well, at the top, they have this thing called the memory cache hierarchy interface, and you see you have multiple connections from the switch boxes or the processing elements through switch boxes to this memory. So as a result, you have contention, and this means that, again, data is second-class citizen. And I basically looked at it and said, it's a rather good idea, not all the way yet. Let's make data a first-class citizen in the project called Cloudchaser. Now, I joined CSCS in January 2019, and Joost, who became my manager, kept pounding on me, Ronald, you need a fully automatic tool chain that allows to compile completely automatically from a high-level language into all the bits that you need in your accelerator without manual intervention. You can build the best accelerator on the planet, but if we cannot compile our code into it, we will not use it. So I took that to heart, and I started to rethink, the architecture that I had kind of already thought about before going to the ETH. But given the fact that I need this fully automatic tool chain, I then, looking at this patent from Al Gara, found that they had this very interesting approach to let a compiler map the DFGs onto the CGRA in a very interesting way. I hadn't seen that before. And the second thing, which was kind of, by accident, but of course in the literature search, you should find these things. I came across a detailed 25-page ACM paper on the graph minor mapping problem, which is kind of what a compiler does when you are mapping functions onto a CGRA. And that together gave me the encouragement to delve deeper into the CGRA. Then CGRAs, you can kind of look at that as it is an FPGA, but at a higher level of abstraction. So an FPGA is a CLB has a programmable gate, so it can be configured to be an AND gate or a NOR gate or something else. It has connections that you can configure between those CLBs. The CLBs sometimes can have a flip-flop as an output. And the CGRA kind of has the same concept, but at a higher level of abstraction. So the functional units are not single bits. They have as input 32-bit buses. And the units can be configured to be a 32-bit float operation, such as an add or a subtract or a multiplication or a literal, and sometimes even a divide. Okay, I had some luck too in this project, but without luck, nobody goes well. So with this, I started what I call the Cloudchaser Accelerator Design Principles. So I mentioned this in the key results a little bit, but to drive this point home, I basically said I must fulfill those three pragmas in my design, which is that to do a sweep across the entire grid for my stencil calculation, I will read the grid point from the DRAM only once. And each DRAM memory read must result in all data from that read being transferred over the bus to be used in the computation. So it cannot fall off the table. In many implementations on CPUs, given the automatic caching systems, you need to fetch an 8-byte pointer. You have a 128-byte cache line, 120 bytes are read and never used because they get evicted out of cache before anybody can ever read them. That is a complete and utter waste of this bandwidth. And then I must have a sustained DRAM read and write at the peak bandwidth. The only thing I will allow is the refresh for obvious reasons. So what we're doing is we're building a domain-specific architecture for a domain-specific language. And we're optimizing this at the die core level and not at the lowest operation level. So we're not optimizing this at the 32-bit add level. No, we're optimizing this at the die core level, including the data motion for fields. And I try to maintain the highest level possible abstraction level to actually ease the whole software tool chain. If I have many, many details that need to be right before it all works, then the tool chain becomes too complex. The result is also that we do an explicit management of the on-chip field cache. So we don't attempt to build a hardware that is intelligent enough to kind of see through the problem. No, it is explicitly managed by the runtime system. But given the DAG of the whole die core, that is actually a simple task. Accelerator DRAM coherency, for instance, through a C6 bus, is at stencil completion only. So in the middle of a stencil, when you look from the host into your DRAM, you will not find intermediate results. If you were to enforce that, it will just eat away from so much performance. That doesn't make any sense. And then at the end of the road, we then vectorize the compute capability in the IJ domain to match the DRAM bandwidth. So the way that I did this is I really started by looking at the data and making all the data work first, and then I sprinkled in the compute at the end to just match how much data we can actually or need to process. So this project has two major areas of work, which is the toolchain part, which is the larger part, and the hardware design part, or the accelerator. And this must be co-designed. So during the sabbatical, I spent, I would say, the first 7.5 months just learning and absorbing the problem, trying to get my head around it. And then only I started to design a little bit in the tool and then a little bit on the hardware, and it went back and forth between the two before I get my final result. In January of this year, the CSCS tool chain looked like this. I don't know what it is currently, since I left at the end of 2019, and given COVID, the discussions are kind of difficult now. But they have a die core that can be described in a domain-specific language that at that time they called GT4Pi, that goes through a tool that can, through an intermediate representation, either go into a Python interpreter so you can check the correctness of your description, or it can generate the C++ code that goes into the Gridtools based solution that runs on their cluster. And basically, I sprung off that path with my tools. And what struck me is that the description that they have captured in this DSL is very nice in that there is a clean and clear separation of the fields, the domain, the iteration space, and the computation. So in many C codes, this is all together in one line of code. You touch all of those things, and it then makes it very hard to figure out how to optimize this. So this is all separated out nicely and represented at a high level of abstraction. Furthermore, for these applications such as COSMO or ICON, the vectorization and parallelization is very well defined and understood. I mean, people have worked on this for decades to get really good performance and good results out of this. And I don't need to add to this. I just need to leverage this. Here I show the requirements for compiling a data flow graph into the CGRA, which is kind of a compiler. And it needs to fully automatically map the data flow graph into a CGRA, so no manual intervention needed. My experience tells me that in that case, I should keep the utilization of the CGRA below 70%, otherwise it will not complete in time. And I use the CGRA as a systolic array, which basically says I get a new result each clock cycle or initiation interval equals 1. There is some startup and result latency of tens of clock cycles, which is acceptable given that the entire compute takes thousands of clock cycles. So this picture shows the principles of operation. Here I have again this section of the DAG of COSMO, which is described at the high level in DICOR domain-specific language that is processed through the tool chain to generate the bits that go into the accelerator, as well as the runtime that runs on the host. The host has already prefetched all of the fields into the accelerator DRAM that are necessary to run the DICOR. And before we run the first stencil, we prefetch those arrays that are needed from this DRAM into my caches that are on chip, which will run at full speed. It will use some couple of barrel shifters in 2D to make it all happen, take some resources, but that's no rocket science. Once the prefetch has been complete, we then run the configuration for this particular stencil in the CGRA for thousands of clock cycles. And while this is done, we've already chosen in the runtime which is the next stencil we're going to run and prefetch those arrays into the caches. All the memories are dual ported, so there's a read port needed by the CGRA to fetch the data, and we can write independently on the write port to prefetch this data. Once the stencil is complete, then the results are written through a write port into a cache, which are now read back into DRAM. And then we repeat that game until the entire DICOR has been done. So here I will skim over how we get the results of the details in interest of time. Basically, this shows a 38 by 38 unit architecture, which is divided into 4 by 4 areas for the IJ parallelization of 4 by 4. The gray and red and green boxes are the SRAMs I mentioned. So the greens ones are the written to, the red ones are read by, and this actually shows an example of a copy stencil. The yellow boxes can be then configured to be either an add, subtract, multiply, mux, literal, or delay for the 32-bit float operation. The compiler that I wrote in single-threaded Python and completes in a couple of minutes shows that we actually have successful mapping for vertical advection forward here, vertical advection backward here, and horizontal diffusion over here with an acceptable amount of utilization and bus length, etc., demonstrating that this is feasible. Again, the insight that stencil computing requires nearest neighbor communication in a cluster enables also doing this at the chip level. My student Kirtana Ravi in TUE in her master project actually studied the wiring problem and came to the conclusion that it's a good idea to have wiring which are a length of 1 to go from 1 PE to the next, as well as 2 and 6 in an optimal arrangement to minimize the number of resources and minimize the hop count. So the data point we chose is this guy to have a maximum hop count of only 4. Performance and conclusion. If I estimate what the performance would be of an ASIC in, say, 10 nanometer, we build it for 128 by 128 by 80 local domain using 32-bit floats. I think we would need 8 by 8 vectorization in the IJ space to match the memory bandwidth of 1 terabyte per second. Transfer of a single field in that case takes 5 microseconds. Horizontal diffusion needs 3 fields and takes 15 microseconds. Vertical advection needs 6 fields and it takes 30 microseconds. That's because there's a forward and a backward part. So if I then compare this to the time that is needed in the GPU implementation, we are about 3 times faster. And an ASIC, I think, would be total about 100 watts. So the conclusion is that this weather and climate accelerator would have a performance that is about 3x wall time better compared to the V100 GPU, and another 3 times better in terms of operation per joule. So the total is then about a 10x performance improvement. We showed that the tool flow is feasible. We showed that the resulting wiring on an ASIC is quite simple and therefore makes that feasible. And I think really interesting is that the performance will scale linearly with the memory bandwidth attached to this accelerator. So it's actually quite simple to calculate the system performance because it's basically the number of HBMs that you have on an accelerator times the number of accelerators in the system, and you can just multiply those numbers and you're done. I haven't found any patents describing this idea of CGRA to implement stencils. The only thing I found that was closest was a cell phone camera application using a CGRA concept, comparing to a Tegra's GPU, where also they showed that it was about 4.5 times better. This architecture actually matches the directions that we have seen in the keynote by Dr. Philip Wong at TSMC at the Hot Chips about a year ago. Now, the next steps are that in the meantime, I retired from IBM. And if you saw the latest news, then you understand even more why that step was right. And I started my own company called Data Motion Architecture and Services GmbH, where I hope to rent myself out to a company that is really interested in making this ASIC happen. I will help to find the funding for this. The company should bring, the desire to make this happen, bring this to market, and a software and hardware design team. And finally, I'd like to have acknowledgements. Of course, I haven't done this in a vacuum on my own. I'd like to start by thanking Professor Thomas Schultes at CSCS for enabling this sabbatical in the first place and his support during. I'd like to thank IBM for letting me actually go. Gagan, he was a good person to talk to, and I thank him for pointing the CGRAs out to me. I thank Algera for a patent that was a point of inspiration. Liang Cheng and Tulika Mitra from University of Singapore for their very nice ACM paper that kind of made the tipping point for me to say, yes, this is a feasible solution. Joost van der Vondelen was my manager at CSCS the entire year, and I thank him for keeping me straight, for challenging me, and for actually widening the application area, because with him we discovered we can go beyond weather and climate, but also address oil and car crashing and many other stencil applications. And then, of course, the Gridtools and GT4Pi teams at CSCS. And finally, Kirtana Ravi, who in our master project made clear that we can have some good ideas to make the wiring for this ASIC really, really simple. With that, I am open for questions.